Now going back to the next part of it. So far what we have done is weird exponential algorithms or model checking. Of course, I would like to do something better, and I'll at least attempt something which is more linear, and therefore we will do something called as theorem proving. The problem remains the same, that a theorem alpha, a statement alpha, R2 or R3 is dishonest, R2 is dishonest is given to me, and I need to prove that alpha holds in KB or alpha doesn't hold in KB, or I need to derive this. So previously we were doing it by all permutation combination, which was called as model checking. Now we will do it by a new technique which hopefully will not have all these permutation and combinations and exponential memory, called as theorem proving. And before that, let me give you two quick definitions. The first one is what is called as a logical equivalence. I say alpha is logically equivalent to beta if and only if alpha entails beta and beta entails alpha. So you say that alpha and beta are exactly the same. There's no difference. So alpha entails beta and beta entails alpha. That's when you say that it's equivalent. There's a harder one, and the harder one is what's called as a validity. I say alpha is valid if and only if it is satisfied in all the models which are possible as per the current knowledge. So if something holds good in everything which holds as per the knowledge, and that's what we are trying to do, we are trying to derive valid facts, not like in some of the cases R2 is dishonest, some R2 is honest, we say dishonest. So we're trying to derive facts which are valid, which hold in all the possible models or which hold in all the possible world, which is different from satisfiable. Alpha is satisfiable only if I can assign some true, some false to honest, dishonest, no good marks, or whatever. And at least in one of them alpha holds, then I say alpha is satisfiable. There is one way at least to make alpha as satisfiable. Like in the AI class, all students are either males or females. Okay, by the way, I'm making a very specific statement for the AI class only. All due respect to the non-binaries as well. So, in the AI class, everybody is either male or a female. That's completely valid. In the AI class, one student has scored 25 in test 1. That's satisfiable. I could say to a student, give him 25 marks and everything will be okay. Nothing will collapse. There's one way to do that. There's some way to make the question paper such that one student, anyone, gets 25. It's satisfiable. It may not be valid. I will make a paper where nobody scores 25. It's satisfiable. Now the two are related to each other. Alpha is valid, or to say they are dual of each other, if and only if not alpha is not satisfiable. So I look at the inverse model. Can I satisfy the inverse model? There's absolutely no way to satisfy the inverse model. That means your model is valid. Similarly, I could do it the other way around as well. Alpha is satisfiable if and only if not alpha is valid. Not alpha is valid, that means the converse always holds good. That means the direct, it never holds. No matter how hard you try, it's not going to happen. There's a second term which is called as a tautology. Something which is always true, irrespective of anything. P and not P is always true. Don't care about anything. P or not P is always true. Irrespective of what you know, what you don't know, there's no way to say that P or not P is false, even sometimes. Okay, so now I'll do it. Some derivations, some deductions, and for that I will need some standard definitions, approaches. The most important one is what is called as oh my god, I make a spelling mistake. It's called as a modus ponens. It's Latin, so you won't get the meaning. It's some mode that affirms, some mode that holds good. All it says is, if I am given alpha implies beta in my knowledge base, I know that, I somehow know that. From my knowledge base, I also know alpha, then I can derive beta. Make sure it's not a divided by. It's logical reasoning. What we know at the top, given this, what we resolve, what we find out, what we derive at the bottom, it's not divided by. So given alpha implies beta and alpha, we resolve, we derive beta, which is of course true. If this holds good, then this has to hold good. Otherwise, the sentence will not hold good. Quick example. So I was given a rule, and that rule very simply meant that bad marks are 1 and I was also given studies AI are 1. It implies honest are 1. This is what I was given. I'm also given the fact that bad marks are 1, and I'm also given the fact that studies AI are 1. All these are facts that I'm given. This is given, this is given. That means by modus ponens, I can derive beta, or I can say honest are 1. And that's exactly what I did. So this is a new fact that I have derived. It's sound, it's come from observations, and this is an application of modus ponens. There's another one which is called as the AND elimination. It simply says if I've given alpha and alpha, then I can derive beta. Like over here, I had been given that studies AI are 1 and studies AI are 2 and studies AI are 3. So I was given R1, R2, R3, study AI. Study is AI R1, studies AI R2, studies AI R3. From there I derive a beta, which is studies AI R1, and that's, if you observe, exactly what I fed around over here. So I had already done the AND elimination. There is also implication. So now this simply means, that means this naturally resolves to alpha implies beta and beta implies alpha. So you'll see I'm stating mostly things which are most obvious. I need not be even telling you these things, to be honest. So whatever you see above is what is given to me, and whatever you see below is a logical derivation that I make because of that. Once I make in all these derivations, another interesting feature comes that information can only be added in a knowledge base. So you go upon studying, you only add information. There's a mathematical way to say this, of course, that I say I had some knowledge base at any point of time, and then this business start. Okay, can I derive something from it? Let's say I can derive alpha from it. Now what happens is that the user, the sensor, gives me a new fact. It tells me something new. It quotes me a sentence I did not know, and there is a tell beta operation. So now what I know is, I know knowledge base and I also know beta. If I could derive alpha before, I will always be able to derive alpha later upon, because its specific leads to generic. By making it more specific, what I'm actually doing is that I'm making it even more easier for the algorithm. Most of the things will get cut because of they don't hold good in the knowledge base. You'll have fewer sentences in that table, and because of that, the subset will be more easily satisfied. I'll have to do less work. So the more knowledge you add, the easier it is to derive, and my knowledge keeps on increasing. And this has a specific term called as the monotonicity, or information monotonically increases as you go along and as you derive in more facts. So now what I'm going to do is I will be using whatever we studied into, of course, some real sense. Now, of course, my entire lecture, all that I have to do is, in my entire lecture, I need to say knowledge base entails alpha by an algorithm A, if you want to add that up, or knowledge base implies alpha, which is equivalent, which translates to knowledge base or alpha. So A implies B, of course, is not A or B. Now, from now onwards, I'll try to do the inverse. So model checking, we took alpha and we tried to prove alpha holds good. Now we'll take exactly the inverse approach, and instead of proving alpha holds, we'll try to prove alpha doesn't hold. And even once, if alpha holds, then I've got a problem. So if my inverse model has even one solution, I have a problem. This is what you have been used to since your schooling as a term called as proof by contradiction. Which is called as that you start, instead of proving alpha, you start to prove not alpha, and if you get something absurd, you say, hey, not alpha can never hold. That means alpha always holds. You get something absurd, and that's exactly what I'm going to do. Instead of proving alpha, I'll have to prove that the inverse doesn't hold good, or instead of saying this, I try to construct the inverse model. Dual, again, I did not take dual, obviously. I need not tell you everything. So in my knowledge base, I add the statement not alpha temporarily. So this is not tell not alpha. I'm temporarily adding not alpha, and I'll see if something weird happens. Or more technically correct, I'll add not alpha and I'll say now my new knowledge base, which is old knowledge base, and this new statement not alpha is not satisfiable. If it's not satisfiable, that means the inverse of it, alpha, is valid. Valid and satisfiability go hand in hand. So in order to prove alpha is valid, I'm trying to prove not alpha is not satisfiable. So let's try to see if we can do it in our old example. And if we can do that, I'll be very happy. So the algorithm that now we study will be called as a resolution. It has nothing to do with the resolution of this video lecture series or the resolution of your mobile phone camera. It has got to do with what I hate, which is in the boardroom meetings with heavy snacks. You don't get it these days. Everybody sits, puts their knowledge, and from the knowledge base we resolve that AI should be taught by Dr. Rahul Kala. That's how I actually got into teaching you AI. In a boardroom meeting, we all resolved, we all decided that AI should be taught with Rahul Kala. Good for you, you've got a new fact. Rahul Kala taught you AI. Okay, so let's get to the example first, and I'll go on to the generics later, which anyways you can get in the book. So I had a rule which said bad marks are 1 and studies AI are 1 implies not honest are 1. Honest R1, my bad. So somebody's got bad marks. He's honest. Let me convert it into not A or B. So it becomes not bad marks R1 and studies AI R1 or honest R1, which of course not will go inside. It becomes not bad marks R1 or not studies AI R1 and or honest R1. Okay, so that is what I am given. I am also given another fact, which is studies AI R1. Now what I say is, now in the more formal form, I merge these two knowledge at one place. So in a boardroom meeting, 1 is given by someone, 2 is given by someone, and we'll resolve something. So I'm given not bad marks R1 or not studies AI R1 or honest R1, comma, which is equivalent to and of the whole thing, studies AI R1. Now what we resolve is the negatives they cut, not studies AI R1 and studies AI R1, the negatives cut each other, so I'm left with not bad marks R1 or honest R2. Wonderful. So that's the third thing that I know. New fact. Let's do it once more. So I also know that bad marks are 1. So let's resolve 3 and 4. So I have not bad marks R1 or honest R2 and bad marks R1. The negatives cut, so I resolve honest R2. I've got new information. Now if you are really into a proof, you really don't need that. I am given studies AI is equal to true. That means I am given not studies AI is equal to false, which means I am given R1, which means I am given that this thing is what is false, and I know false or A or B or C is nothing but A or B or C. In or you can eliminate false, in and you can eliminate true. And that's exactly what I've done. I've eliminated the false one. I knew the ground truth. I knew what it was. I can just eliminate that up. And by eliminating that up, this is exactly what I have received. Now I may just do it once more. I had not honest R1, I had not honest R2, I had not honest R3, I know honest R2, so R1. So negative scar, that means I resolve a number 6 over here, which is not honest R2 or not honest R3. Similarly, I'll derive number 7 by a similar process, honest R3. So if I resolve 6 and 7, it becomes not honest R2 or not honest R3 and honest R3. That means what do I resolve? Not honest R2. Now let's say my theorem that I needed to prove was that R2 is honest. Somebody told me R2 is honest. I say, okay, let me try to prove that R2 is honest. Let's do it the other way around. Somebody told me R2 is dishonest. I say, okay, let me try to prove R2 is dishonest. That means I add not alpha to KB, or I add honest R2 to KB. Now I resolve 9 and 8, which is not honest R2 and honest R2. The negatives cut and I get a null. That means I go nowhere. I go absolutely nowhere, and because I go absolutely nowhere, it means this model is not satisfiable. I've ended up in being false or false, and somehow I need to make it true. So there's a statement not honest R2 which I derived, and honest R2, and I somehow need to make it true. It's not possible. That means this model is not satisfiable. That means there is no solution. That means not alpha that I added is wrong. That means R2 is dishonest. And this is what is the resolution.